Good to have you back. So today I'm going to address two issues. One is a little more on the z-scores, and the other one is how to relate the binomial distribution, which happens to be a discrete distribution, to the normal distribution, which is a continuous distribution. There is a link, and there are a couple of conditions. So let's go back to the problem we did before, which was you have IQ scores. They follow an approximately normal distribution. It's given to you. You don't have to figure out whether or not the distribution is normal. We gave it to you. Obviously, we have to give you the two parameters, the mean, 110, and the standard deviation of 25. The picture looks like this, okay? So 110 is in dead center. The standard deviation is 25, which is the distance from the center into the point of inflection. So if you go down, you should get 110 plus 25, which is 135. And if you add two standard deviations, you get to 160. If you subtract one standard deviation, you get to 85. If you subtract another one, you should get 60, and so on and so forth. So what is important is the mean, the standard deviation, and what does the axis stand for. It stands for IQ scores. I call this X, okay? So a question which is extremely similar to the ones we've done before. I'm not doing it for review. I'm doing it to do something else, okay? So what percent? We're looking for a probability. We're looking for an area under the curve. We're looking for a percentage. We're looking for a ratio of people have scores between 85 and 160. So here is 85. Here is 160. These are positions, locations. What's the percentage or the probability that if you pick up one person at random, their score is going to land between 85 and 160? And that is precisely the area under the curve between 85 and 160, okay? From here all the way to here. So that's area. Now we know how to do it. First of all, the question becomes this question. The probability that X is between 85 and 160. We have already addressed whether or not 85 should be included or not included. Same thing with 160. Nobody cares. Whether you include it or you don't include it, the area under one number is always zero anyway. The probability that X equals 85 is precisely zero. So whether I write more than 85 or I write greater or equal to 85, they're going to have to be the same anyway. So it doesn't matter whether or not you put an equal sign, okay? Put the equal sign, don't put the equal sign, nobody cares. In other words, you're looking for the area between 85 and 160. Now, whether you put dashes here or a solid line, dashes here or a solid line, it doesn't matter, okay? And the way you do it, it's norm CDF, obviously, because we told you it's normal. And you have to put the interval from low to high, mu, sigma. So mu is given to you, sigma is given to you. I found that probability is about 81.86%. All it means is if these numbers are true, and I think they are, if I walk around the US, just randomly walk around and grab one person at random, what's the chance that that person has an IQ score between 85 and 160? That chance is 81.86%, close to 82%, which is fairly high, okay? Now, and that's not surprising because between 85 and 160, the mean is right there. It's in that interval. So that consumes a lot of space here, right? So that's why it's very high. Now, I did this. I know you know how to do this, but I did this to invoke the idea of the z-score. So I put the formula again in green. So if I have an X, I should know the Z. How do I standardize? I'm going to pause here. Last time we talked about z-scores. Sometimes we call them the standardized scores. You wonder why like the SAT exam, it's called standardized exam. Isn't that what it is called? Standardized tests. The reason we like z-scores is because they standardize everything. For instance, let's say at your school you get an A in English, okay? And a friend of yours in a different class with a different teacher gets a B. And another student in a different school, could be public, could be private, get a B or a C or whatever. And a students from across the states, maybe you live in Texas, and another student in New York City get a B plus. There is no way you could rank those students and say, well, the kid who got an A first, the very first student I mentioned, is a better student. Because you have different teachers, different schools, different states, maybe public, maybe charter, maybe private school, we don't know. And maybe my teacher is a hard grader. Maybe I'm stronger than you, I got a B, and you got an A, but you are with a teacher who hands out easy grades, right? So that's not fair. So what do we do with those 4 students and everybody else? We standardize the scores. In other words, if you take an SAT exam this year and you get, let's say, 700, and another student this year, it doesn't matter what school they go to, what teacher they had, what state they live in, what type of a school they go to, and they got 650 and you got 700, you definitely performed better. Why? Because the SAT exam or the ACT or even the AP exams are standardized exams. So the Z score, what it does, it standardizes the numbers so we can compare apples to apples. That is the whole point of the Z scores. And I'll say more about it in a minute. Okay, so what if I change this into Z values? So for example, if I pick 110, which is the mean, I'm just picking numbers at random. If I pick 110, I should get a Z of 0, right? Because 110 minus 110, the mean is 110. 110 minus 110 is 0, and 0 over a positive number is 0. Now, let's test 135. And I'm claiming if x is 135, z has to be 1. And I'll show it to you. I'll give you 2 reasons. One is, let's just plug in 135. So 135 minus 110, remember the mean is 110. 135 minus 110 is 25. And 25 over 25 is 1. That's one way to do it. Another way to do it, when you look at this 110 and the standard deviation is 25, so when I add 1 standard deviation, by definition, the z-score is the number of standard deviations you are moving away from the mean. So if I am at 135, how many of those did I add to 110 to get 135? I added 1 of them. And therefore, z must be 1. See? Z here is 0, z here is 1. Imagine I have another curve, and the mean is 200, and the standard deviation is 10. If I standardize this curve here, that I don't have, if I standardize it here, and I standardize the black one into this blue, then I can compare the 2 blues. That's what I was trying to say earlier. So if I standardize this curve, it looks identical. Literally, the area between here and here is exactly the area between -1, and I'll talk about -1, between -1 and 2. Because I'm going from 85 to 160. If I look at 160 here, 160 minus 110 is 50. 50 over 25 is 2. It makes sense. 160 is 2 standard deviations away from the mean. Therefore, z must be 2. So This is like your first name, your last name. They look different. That is a number in black and it has 3 digits. This is a number in blue, it has 1 digit. But they represent the same position, the same location. All I did to 160 is I standardized it. All I did to 135, I standardized it. All I did to 110, I standardized it. All I did to 85, I standardized it, which means I found the z-score based on the x value. That's what standardize means. Standardizing means going from x to z. So if you look at 85, notice 85 is 25 units below 110. If I subtract 25 from 110, I get 85. So I suspect z score for 85 has to be -1. Well, if I put 85 minus 110, I get -25. And -25 over 25 is -1. So this is called normal distribution of IQ scores. And this is called the standard normal. The standard normal. They are identical, except that the numbers look different. But the areas are the same. The area from here to here is the same thing as the area from -1 to 2. So if I change the x values into z values, I'll be looking for the probability that z is between -1 and 2, which is identical to saying the probability that x is between 85 and 160. To go from 85 to 160, it's like going from -1 to 2, as far as z is concerned. So how do we do that? Normal CDF again. Norm CDF, interval, -1 all the way to 2, -1 all the way to 2, and then the mean is 0, and the standard deviation is 1. Now, whenever you deal with z, by the way, whenever you deal with z, the mean is always 0. And the standard deviation is always 1. In fact, if you go to the TI, to your grapher, and write norm CDF interval from -1 to 2, like this, right? -1 to 2, which is exactly from 85 to 160. You don't even have to write 0, 1. Whether you write it this way or you just write the interval, you don't even have to say mu sigma. You don't have to write 0, 1. You will get the same answer. See? So remember, let's say this is for IQ scores. And let's say I have another normal distribution for something else. And I will standardize it. So I can compare my new standardized curve to this new standardized curve. You don't want to compare apples to oranges, but you want to compare apples to apples. Make sense? So Z means standardize, please, the X values. Standardize X to get the Z so we can talk apples to apples. Okay? So that's the whole point of the the Z scores. This is called standard normal distribution. This is just normal distribution. This is called standard normal distribution. Okay, now I'm going to shift gears and do something different. Recall a week ago or so, we talked about the binomial distribution. I had 20 light bulbs. I had a probability of success. I had probability of failure. The 4 conditions were fulfilled. 2 outcomes, the probability doesn't change. Of P and Q, they don't change. The events are independent. 1 light bulb defective has no effect on the other. The number of trials is fixed. These are the conditions for the binomial. And one of the questions we did, if you remember, was what's the probability that at most 18 light bulbs are non-defective, they're good. What's the chance out of this 20? What's the chance that 18 or less, maybe 17, maybe 0, maybe 1, but no more than 18 are non-defective? I choose to use binomial CDF because I already have less or equal. And remember, the binomial CDF loves less or equal. So we just do NPX. These are the 3 parameters. And like the normal distribution, we write interval, mu, sigma. Interval, mu, sigma. For the binomial, we write npx. So n is 20. The probability of success is 0.8. And the number in question is 18. So this reflects this. And if I compute that probability, I got at least 93%. So if I have an 80% chance of picking one light bulb at random, and I find that it is good, it's not broken, it's not defective, right? And only 20% of them are bad, what's the chance? And let's say I have 20 light bulbs. What's the chance I have at most 18 light bulbs non-defective? Maybe all of them non-defective, maybe one non-defective, maybe two, all the way to 18. It's going to have to be high. And that chance is 93, a little over 93%. Now, mathematicians decided the binomial distribution is discrete. It goes like this: 0, 1, 2, 3, all the way to 18, 19, 20. There is no 18.1 light bulbs, okay? The distribution of the binomial, we call it a discrete distribution. If you put less or equal versus just less, there is a huge difference, right? A number less than 18 cannot be 17.9999. It has to be 17, right? That's discrete. And mathematicians decided, it's always nice to work with continuous distributions, and I'll explain that in a little bit. Can we approximate the binomial by a normal distribution? And the answer is yes, so long two conditions are fulfilled. What are those two conditions? If NP and NQ are more than 10, we can assume this is normal as well. And if it is normal, I can just do exactly what I did here. Well, let's test. What's NP? NP is 20 times 0.8, which is 16. That's more than 10. Good, checked. Let's check NQ. NQ is 20 times 0.2, which is just 4. It's not more than 10. So the two conditions, one of them was violated. Therefore, we're not supposed to approximate the binomial with a normal distribution. We're not supposed to. Because you're going to have an error if you decide to take that leap, right? You can't take that leap of faith. Because one of the conditions was violated. Both conditions have to be fulfilled so that we can assume that this binomial distribution, and I know we checked the four conditions, we know it's binomial, we can use the idea that it is normal as well. You might say, why do we care? Why do we have to approximate a binomial by the word normal? Why can't we just stay here? Let's leave the binomials alone and leave the normal distributions alone. Why do you want to mix them? Well, as you will see in the future and even today, working with continuous distributions is always much easier. And if you take calculus, you talk about continuous functions, and continuous functions are much easy. Not only easier, they are much more useful than the non-continuous functions. So I decided, I've never done this by the way, I decided, even though the violation is there, I decided to approximate to see how bad my percentage is going to be. It's not going to be the same. So if I decide to call it, okay, let's just approximate anyway, even though we violated one of the rules, let's just approximate. I love this idea of what if. We know we're not supposed to, but what if? Let's just do it for fun. Okay, so the question is this, right? Same. What's the probability that x is less or equal to 18? Well, remember what it writes, interval mu sigma. Well, the interval, this is less or equal to 18, looks like this. You come from negative infinity all the way to 18. That's what less or equal to 18 means. So the interval is a negative number that is big all the way to 18. I wrote negative 10 to the 8, which is like negative 100 million. Feel free to write negative 1,000 all the way to 18. But now I am faced with a serious problem. And that problem is, well, how the heck am I supposed to find the mean and sigma? Nobody gave me the mean and sigma. We know we're going to need the mean and sigma for normal. Well, there is no mean. There is only P and Q. There is no mu. There is no sigma. Well, if you take statistics in high school or in college, you will find out that the mu is actually NP. So NP is just 16. 20 times 0.8 is 16. And standard deviation is the square roots of NPQ. So if I multiply 20 by 0.8 by 0.2, and when you finish, you take square roots, I got about 1.789. I think I got like square roots of, 1.789. Now that I know mu and sigma, I'm going to plug them in. See? Mu, sigma, interval. I got 86.82% chance. If I pick one light bulb at random, what's the chance that what's the probability that at most 18 light bulbs are non-defective? I found 86.82%. The truth of the matter is, this is the answer. And this normal distribution, it did not do a good job. Good job means I should get an answer close to this. It's not going to be exactly, this is the correct one, okay? I'm supposed to get something close, but I didn't, as expected. Why? Because we violated one of the rules. If the rules are not violated, I can guarantee you that you'll get something close, maybe 93% or 93.5% or 92.99%, something close to this. It's not going to be exactly this, but it's going to be close. That's why we say approximation, normal approximation of the binomial distribution. So I did expect a number to be off, and yes, I did get it. This is not that, okay? Now what I want to do is cook up an example where both conditions are good, okay? So I'm going to change something. One of these three things I'm going to change, maybe more. Watch. So I change n into 100 now. So we have 100 light bulbs. And you got so used to P and Q equals 0.8, 0.10, 0.2. I changed them, okay? Just for fun. So let's say the probability of success, which means finding non-defective light bulbs, is 0.7. And the probability of finding a defective light bulbs is 30%. So NPQ. Let's just work with binomial. Okay, I changed the question on you. What's the chance that more than 60 are non-defective? Well, remember, CDF hates more than, likes less or equal. Well, the complements, imagine this is, I'll put it here. This is 60 all the way to 100. This is 0, this is 1, right? More than 60. More than 60 means this. What's the complement of this? The complement of this is the stuff in green. Right? So the probability that X is more than 60, which is this stuff in red, is 1 minus the probability that X is less or equal to 60, stuff in green. And now I'm happy. I like this, right? So it's 1 minus, and so what's this? Remember, the parameters are NPX. N, what did I do? I screwed up. I did the math correctly, but I wrote something wrong. So this should be N. N is 100. I think I was trying to approximate with the binomial, with the normal distribution. N, N, P, X. So I hope I'm not wrong, I got 1 minus this, I got 97.9%. Got it? That's what I got. I'm just working with the binomial distribution. The same scenario of light bulbs, so they fulfill all the 4 conditions. Okay, now let's see if we can approximate with the normal. Well, The only thing we need to do is check NP and NQ. Now NP is 100 times 0.7, which is 70, definitely more than 10. And NQ is 100 times 0.3, which is 30, definitely more than 10. The condition has to be more than 10, okay? So they are fulfilled. So I'm going to pretend this question, this x follows a normal distribution. So here is the question again, same question. What's the probability that x is more than 60, assuming x follows a normal distribution? Well, remember what this is. We write interval mu sigma. The interval, we said more than 60. That means 60 all the way to some big number. I don't care, again, I don't care if you put an equal sign, don't put equal sign. Nobody cares for continuous functions. Okay? In here, it does matter. See, in here I have more, in here I have less than. If you just write less than, you'll be wrong, okay? But when you deal with normal approximation, normal distribution, it doesn't matter if you have this or this. It doesn't matter if you have this or this. They're the same, okay? Because the area does not change. Okay, so I'm going to assume it's normal now because the two conditions were fulfilled. So I'm going to do norm CDF interval. The interval goes from smallest number to the biggest number, right? And then I need mu and sigma. I showed you how to find mu and sigma. Mu is NP. NP is 70. I just did it. We knew the answer anyway. And standard deviation is square root of NPQ. So square root of 100 times 0.7 times 0.3. I got 4.58. If I remember correctly, I got like square root of 21, which is 4.58, give or take. Okay, so I put 70 here. I put 4.58 here. That's mu, that's sigma. I put them in green so you can track your numbers. And I got 98.54%. Not too bad. Look, that's the right answer. That is the approximation. It's not bad. As compared to this one, huge difference. Why? Because one of the conditions was violated. In here, both conditions were okay. I expected to get a number close to this number. I got it. Now, I didn't know if it's going to be a little bigger or a little smaller, but I do know that it is close. I think this is close enough. Okay, 97.9%. That's basically 98%. And this is 98.5%. Not bad. Not bad at all. Okay, and I wrote it here. All right, so that takes care of the normal approximation to the binomial. Now, I am going to go back to the z-score for fun. What if I decide, this is normal, right? What if I decide to standardize this number, 60? Well, if x is 60, we know mu is 70, and we know the standard deviation is 4.58. If I do that, if I plug in 60 minus 70, this one, divided by 4.58, the corresponding z-score is negative 2.18. So this question is precisely this question. The probability that x is more than 60 is the same thing as saying the probability that z is more than negative 2.18. Notice that this 60 is less than the mean. It's to the left of the mean. So you expect the z-score to be negative, and it is. Notice that the standard deviation is not too big. In other words, look. If this is 670, and the standard deviation is 4.58, so if I take one standard deviation, I get something around 65.42. If I take another standard deviation, I get 60 point some change. I don't know, 60 point some change, right? And I'm asking, what's the chance that x is more than 60? Notice that 60 is approximately negative 2 z. Z equals negative 2, kind of. And that's why I got negative 2.18, okay? Let me fix this. more than 60. You don't have to do this, by the way. You don't have to standardize. But I thought since we worked on it here, this is the same thing as this. It's good to practice. So this question is exactly this question. So now, what's my interval? My interval is from negative 2.18 all the way to some large number. My mean is 0. Remember, you cannot write 70 and 4.58 anymore. For the standard normal, whenever you deal with z, the mean is always 0 and standard deviation is always 1. Remember what I did here. It's always 0, the mean is always 0 for z, and standard deviation is 1. So you could do that. Or if you're lazy, don't even write 0, 1 at all. Just that, just the interval. You will get the same answer, okay? So these are two good approximations to the actual correct answer. This is the actual correct answers. This is approximation. Now you say, I'm gonna finish with this. Why do we care to use normal? Why do I have to approximate when I can get it correctly on the spot? Why do I have to go through trouble not only to improve, but actually not improve? Because this is the right answer. This is an approximation. The reason is, imagine, let's go back to binomial. Okay, let's say I have 100 light bulbs. And let's say P is 0.7 and Q is 0.3. Okay? Let's say I said find the probability that X is more than 70. Okay? Now, if you do this by hand, you'll drive yourself nuts because you're going to have to do, well, it has to be 71 or 72 or 73, ... all the way to or 100. Isn't that what it? And each one of them is a nightmare, right? 100, choose 71, 0.7 to the power of 71, 0.3 to the power of leftover. And this one is a nightmare, and this one is a nightmare. And there are like 30 of them or 31 of them. That's a nightmare. You might say, okay, that's bad. Okay, I don't want to do that. Why don't we use the complements? Okay, well, let's look at the complements. So here is, let's just for fun. Okay, so this is 0, this is 1, this is 70, let's say, this is 100. More than 70 means these guys. The complement would be 1 minus the probability that X is less or equal to 70. Because 70 was not included initially. Remember, this is different from this with discrete distributions, unlike the normal. Okay, so strictly more than 70 means this stuff. The leftover is this. So X is less or equal to 70. Well, that is also a nightmare. Because what does it mean to say the probability that X is less than 70? It could be 0. It could be 1. It could be all the way to 70. And there are 71 terms you have to do. And each one of them is a nightmare. To do, let's say this one is 100, choose 1, 0.7 to the 1, 0.3 to the 99. That's just this one, and this one, and 2, and 3, and 4, all the way to 70. So we don't like it. We said, you know what? If NP and NQ are both more than 10, and I can approximate, it'll be a joke. It'll be so easy. I could just do norm CDF interval mu, which is NP, sigma, which is NPQ, square roots, and you're done. Okay? We love to work with normal distributions. In fact, we love to work with continuous distributions. We do not like to work with discrete distributions. Sometimes we have no choice. We just work with discrete. But as far as the binomial, it can be approximated by the normal. Not every discrete can be approximated by continuous, by the way. But as far as the binomial is concerned, it can be approximated by the normal distribution under the conditions that NP and NQ are both more than 10. Makes sense? All right, so I am going to conclude with a very nice, I don't know what's happened to me. Here you go. With a very nice assignments. So I am not going to give you math problems today for fun. You've been working very hard. So I'm going to give you brain teasers, 2 of them, but this is your assignments. In the past, I've said, feel free to do the brain teasers, do them, don't do them, nobody cares, because I gave you homework. Well, today I'm not actually giving you math homework. I'm going to give you brain teaser homework. So all you have to do is work with these 2 fun problems. It's coming, summer is coming to an end, so I thought that'll be nice to you. So here is the very first one. Please make sure you submit your assignments, okay? This is not optional. Make sure you submit. And it doesn't matter if you're incorrect, but I want you to give it a try. So imagine I have a shovel. It has 4 pieces. 1, 2, 3, 4. And they're movable, those 4 pieces. 1, 2, 3, 4. And you have something in the middle, like a rock. What I would like you to do is move 2 sticks, no more than 2 sticks out of these 4, to make the picture look like this. Basically, the rock has to be outside. So for example, you might say, okay, I am going to erase this, and I'm going to move it here. And I'm going to erase this, and I'm going to move it here. Well, it's true that the rock is outside, but this is not a shovel. Makes sense? I'll try another one. Let's say this is my shovel, 4 pieces. And you say, oh, I think I got it. I am going to move this piece here and put it here. And take this piece here and put it here. I did maintain the shovel. The problem is the rock is still inside. The rock has to be outside, okay? And as a hint, as a big hint, don't even touch the rock at all. Don't touch it. Just take 2 out of these 4 pieces and move them somewhere to make this picture look like this without even touching the rock. Okay, so that's the first question. Second one is fun. So I have an electric train traveling north, let's say going in this direction, at 60 miles per hour. But the wind is blowing in the opposite direction at the same speed. And I'm asking for the direction of the smoke. In what direction is the smoke going? Is it going north? Is it going south? Is it steady because the wind is moving in this direction and you are going in that direction? Is it going upward? I want you to think about this. Remember, this is a brain teaser. So none of the answer I just gave you is correct. It's a brain teaser. It's supposed to push you to think a little bit, okay? You don't have to do any math whatsoever. And by the way, every time I give this to young kids, they get it. And every time I give it to multivariable calculus students, they start drawing vectors. I have a vector function, a vector v going north, and I have another vector called w, which is the wind, going south. And they start playing with vectors and adding vectors and doing all sorts of stuff. None of that stuff is needed, okay? So that should end today's presentation. Please do these two questions and submit them for fun. It should take no more than 10 minutes because the video is about 38 minutes. So I hope you listen to it carefully and you understand the normal approximation to the binomial, and you understand the importance of standardizing curves, which means finding the z-scores that correspond to x values, so that you can make better decisions with data in the future. Take care.